Welcome. Today, we're diving into the chemistry of alcohols. And really, it's all a story about one tiny two-atom group that has this massive impact on pretty much everything, from the sanitizer on your hands to the antifreeze in your car.
So, let's start with a little riddle. What could hand sanitizer, a glass of wine, and engine antifreeze possibly have in common? I mean, they're three totally different things, right? But believe it or not, they share a deep chemical connection. Any ideas?
And the answer is a class of molecules called alcohols. Yep, they are the chemical workhorses doing the heavy lifting in all three of those products. Today, we're going to figure out exactly what makes them so incredibly versatile. Okay, so at the very heart of every single alcohol molecule is this little superstar right here, the hydroxyl group. We just call it the OH group. It's so simple, just one oxygen atom bonded to one hydrogen atom. But as you're about to see, this tiny group is the hero of our story. It dictates everything about how an alcohol acts.
So, if alcohols are in so many different things, how on earth do chemists keep them all straight? Well, it all starts with having a really clear system for how to classify them.
To make sense of this huge, sprawling family of molecules, chemists use a couple of simple systems to sort and organize them. Let's take a look at the first one.
The first way is super straightforward. You just count. If a molecule has only one of those hydroxyl groups, like the ethanol that's in wine, we call it monohydric. If it has more than one, like the glycol in your car's antifreeze, it's polyhydric. Easy enough, right?
Now, the second method gets a little more specific. We look at the exact carbon atom that the OH group is bonded to, and then we count how many other carbons that carbon is attached to. This gives us what we call primary, secondary, and tertiary alcohols. Now, this might seem like a tiny detail, but trust me, it completely changes how the alcohol is going to react chemically. It's a huge deal.
All right, so now that we know how to sort them, how do we name them? Let's learn the universal language that chemists use to talk about these molecules. It's called the IUPACE system.
It might look a little intimidating, but it really just boils down to 4 simple steps. First, you find the longest carbon chain that has the OH group on it. Then, you number that chain so the OH gets the lowest possible number. Step 3, you name any little branches hanging off the side. And finally, you just put it all together. And here is the most important part. The name always ends with "all." That's the universal signal for, hey, this is an alcohol.
And here's a perfect example of this system in action. What most of us call rubbing alcohol, or isopropyl alcohol, is known to chemists as propan-2-ol. Let's break that down. Prop for 3 carbons, an for single bonds, and 2-ol tells us the hydroxyl group is sitting on that second carbon. See? It's a perfect logical description in a single word.
Okay, so we can sort them and we can name them. Now for the really fun part, how do we actually make them? I want you to think of this section as a chemist's cookbook with 3 of our favorite recipes. Our first recipe is called hydration. We start with a molecule that has a carbon-carbon double bond, and basically, we just add water. The water splits and attaches itself across that bond. Now, this doesn't just happen randomly. It follows a famous guideline called Markovnikov's rule, which pretty much says the hydrogen atom from the water will go to the carbon that already has more hydrogens. You can think of it as the rich get richer. So what if you want to break that rich get richer rule? Well, that's where recipe number 2 comes in. It's called hydroboration oxidation, and it's the chemist's way of being a rebel. It also adds water across a double bond, but it does it in the complete opposite way, giving us what we call the anti-Markovnikov product. Having this kind of control is incredibly powerful. And this is where it gets really, really cool. Let's say we start with the same simple molecule, propylene. If we use recipe 1, we follow Markovnikov's rule and we make propan-2-ol. That's our rubbing alcohol. But if we use recipe 2 instead, we get propan-1-ol, a completely different alcohol with totally different properties. Same starting material, different recipes, different results. That is the power of synthetic chemistry right there. Our third recipe involves a very special tool called a Grignard reagent. Think of this thing as a molecular construction kit. It's a fantastic way to add new carbon atoms to a molecule and build bigger, more complex alcohols from simpler starting materials like aldehydes and ketones.
And check out this handy guide. It's like a cheat sheet for making alcohols. Depending on what you start with, you can precisely control what kind of alcohol you end up with. You start with formaldehyde, you get a primary alcohol. Use any other aldehyde, you get a secondary one. And if you start with a ketone, boom, you get a tertiary alcohol. It's an amazingly precise and predictable tool to have. So, we know how to classify them, how to name them, and how to make them. But why do they behave the way they do? Let's unlock the secret behind their chemical superpower.
So what is the secret? Well, you're not going to be surprised when I say it all comes back to our hero, that hydroxyl group. You see, the way electrons are shared inside that tiny OH group makes it polar, which creates a slight electrical charge. And that little bit of polarity is the source of all of an alcohol's superpowers. And that superpower has a name: hydrogen bonding. Because of that polar OH group, alcohol molecules are strongly attracted to each other, kind of like tiny little magnets. Now, this isn't a true chemical bond holding them together, but it's an incredibly strong force between molecules, and it has some huge consequences.
And the first major consequence of all these tiny molecular magnets holding on tight to each other? You get unusually high boiling points. I mean, just look at the sheer scale of the difference here. Ethane is a molecule that's a similar size to ethanol, but it doesn't have that OH group. It boils at a freezing cold -89 degrees Celsius. Now add that one little hydroxyl group to make ethanol, and the boiling point skyrockets all the way up to +78 degrees. That's the incredible power of hydrogen bonding, literally holding those molecules together.
The second superpower is solubility. So why does alcohol mix so well with water? You probably guessed it, it's hydrogen bonding again. The alcohol's -OH group can form those same magnetic attractions with water molecules, which lets them mix together perfectly. But, and this is a key point, as that carbon chain gets longer and more kind of oily, it starts to get in the way, and the alcohol becomes less and less soluble.
And that really brings us to the main takeaway. If there's one thing to remember from all this, it's that everything, from their names and classifications to the recipes we use to create them and their surprising physical properties, it all traces back to that one simple, powerful little structure, the hydroxyl group.
It's really incredible when you think about it. Just a tiny change, 2 little atoms, can have such a massive impact. It really makes you wonder, doesn't it? What other small atomic tweaks are out there, responsible for the incredible diversity of the world all around us? Thanks for joining me.